we should know, as a review from yesterday, guys, but also just what we've been doing all year long with reactions. The forward reaction is where we go left to right. And then the reverse reaction is the opposite. It's right to left. So we've got to start thinking in terms of not just normal reading left to right, but right to left as well, because all of these equilibrium reactions can go forward and backwards. Then we introduced that term activation energy yesterday, where it's going to make more sense. You'll visually kind of see what that is, but what it means, guys, in terms of a reaction, how it applies, it's the amount of energy that's needed to get a reaction started. So it's kind of like this threshold. You've got to kind of overcome this hill. All right, if you're walking up a hill or you're riding your bike, all right, you see this giant hill and it's awful, but when you get to the top, after that, what do you have to do? You just coast, right? It's easy after that. So that's kind of like a reaction in terms of energy. We've got to put all this energy into the system, but once we get to the certain top point, it's coasting from there on out. So what this shows, guys, and these are just general graphs that show what happens overall in a reaction. Okay, they're not necessarily specific, counting up all the different energy within the different spots of the reaction. All right, we're not able to do that. So it's just a general idea to give you a better understanding of what's going on within a reaction. Okay, and we're talking about the pathway. The reaction pathway, is that just one step always? No, it can be multiple steps in it. Your reaction is only as fast as what? A reaction is only as quick as its what? Slowest part. What do we call the slowest part in a reaction, guys? The rate determining step, okay? That's what's going to dictate it. So that slowest step in your pathway is going to dictate how fast the reaction is. So you've got to be able to label certain parts of this graph or be able to know where they are to be able to answer questions on them. All right? So we're going to go through and we're going to label all of this part in here today. So let's first start off on the left-hand side, guys, with our y-axis. We're just going to write some values in there. These could change depending on the reaction, so we're just going to put some different terms in there just to kind of have some energy pieces. So we're going to say 10 kilojoules. Of course, that's going to happen. We're going to just say this is going to be 45 kilojoules. This is obviously not to scale, and then we'll say 100 kilojoules.
What does it say on the bottom?
10 kilojoules. All right. So, Tony, you can just kind of go through and sketch this. I would encourage you. Yep, perfect. Okay. Now, this is showing potential energy, guys. So anywhere below the line, this line that we have going through here, this is showing the energy that is involved within this reaction. So first off, let's just kind of identify what type of reaction. From looking at this graph, what do you guys think? What type of reaction do we have here? And I'm not talking single replacement or synthesis like that. I'm talking endo or exothermic.
Exo.
Why do you say exo, Jill?
The release of energy.
Yeah, release of energy. Now, it doesn't necessarily, if you think about it, look like it's releasing it, but look at where we start. We start over here at 45 kilojoules, and we end up with 10 kilojoules. So we're losing energy in this reaction. Therefore, this is an exothermic reaction. Okay? Which means our reactants, again, that we start with, and are higher in energy than our products are. Products end up lower in overall energy. Right? So anywhere below the line, guys, that's showing or measuring our potential energy. So right here, if I were to draw this arrow in here, from that line to the bottom, that's going to be my potential energy of my reactants. You will be asked questions, and you'll see as we get into practice today, what's the potential, how much potential energy do the reactants have, or how much potential energy do the products have? So you've got to know where those different pieces are throughout this. These are the kind of, we're starting off with the basic pieces, all right, that make sense. And you'll see some different components as we go along. Okay, so below the line, that's our potential energy of our reactants on the left, and then the potential energy of the products on the right. So like you were describing from your experience with this, looking at these pathways, guys, that's the highest point right there. All right, that point is a specific point. Think back to our definition of activation energy. Okay? that we were just talking about. It's the energy needed to get a reaction started or to form the activated complex. That's this point right here, guys. This is our activated complex. That is the highest energy point in our pathway. That's an important piece that you will have to know where it is. All right? If I drew an arrow like this all the way to the bottom, what do you think that arrow is symbolizing, guys? Of what? It's going to be potential energy because it's below the line of what? A specific point. What point is that arrow pointing to? It's the activated complex, guys. It's the potential energy of our activated complex. The overall graph that we have here, guys, that's showing the potential energy of the reaction. Okay? Because it's not, the reaction is not just one point. It's fluid along this entire graph. All right? So these are specific points that we're looking at here. Now, let me ask you this. What do you think this is? Is that going to be measuring potential energy of any point in the reaction, that arrow that I just drew in? So what do you think that is, guys? Energy gained? What are we going to call it? Because think about the point that where it starts and where it ends. What's it pointing to? Notice there's the dotted line in there, right? What is even with that dotted line? The activated complex. So that's showing a difference from we start at 45 and we get up to 100 kilojoules. What do you think that is, guys, that arrow is representing from what we've already talked about today? That's our activation energy, okay? This is our activation energy of our forward reaction. And I just spelled activation. I don't even know what I was spelling. Activation. Now I'm putting in there the forward reaction. Is that going to be the same as the reverse reaction? No, we'll get that in a second. Guys, a symbol for activation energy is capital E with a subscript A. Okay, capital E with a subscript A. If you can't read anything up here, just shout it out. Okay, let me know. Because I know it's kind of small that I'm writing, but it's so you can see it all. What's this arrow representing, do you think? Absolutely, guys. So this is where you got to start thinking about it in forward and reverse. It's the same thing. On top of our big pathway line showing potential energy for the reaction, if it's on top, guys, it's the arrow. It's the difference trying to get over the hump. So this is going to be our activation energy of our reverse reaction. So it's not good enough to just think, oh, I'm reading left to right all the time. You could be given an exothermic graph like this, but then they can say, well, what's the activation energy of the reverse reaction? Okay? So tell me, what is my activation energy? What's the numerical value, guys, for the activation energy of my forward reaction? How do you figure it out?
55.
Right. 100 minus 50 or 45 gives you 55. The reverse reaction would be 90. So that's how much energy you have to put into the system to get the reaction to go. Now, do you get, with the forward reaction, guys, when we look from left to right, do we get that energy back with the forward reaction? No? You sure? Take a look. We have 45 kilojoules to start. We put another 55 in to get to 100, so we don't get any energy back. Where do we end up with at the end? 10. So guys, this is exothermic, so it is being released. 90 kilojoules is being released, so we're ending up with less. And that's our definition of an exothermic. We put in 55 kilojoules, but we can reclaim that and get that back out. Now, typically, you're thinking, oh, exothermic reaction is just going to go off into the system. Absolutely. But if we did this in a system, guys, a closed system, that's going to be in there that we could then use for something else if we wanted to go back and forth. Because think about it. These are reversible reactions. Okay? So it's staying within our system, showing that, hey, exothermic, it's releasing that. It's not just staying in there all the time. It's like that roller coaster. You got to build up, but then it goes fast after that. This is the hardest part because it's got to take that energy in. All right? What if I did this? I'm going to change colors. What does that orange line represent? Any ideas? Okay, just because I drew this orange arrow over here more to the right, it's the same difference, guys, as what it was right here with our activation energy. So having those dotted lines, if you're not given dotted lines like you're going to see in your practice today, draw these 3 dotted lines in like we see here. One that's at the top, one that continues on from the reactants, and one that's for the products to kind of give you some reference points to those different pieces that it's talking about. Now, let's take a look here at this arrow. This is the one of the last ones that we're going to do. What's that showing the difference of, guys? It's between what 2 lines? Where my reactants are and the products are. So that's a difference there. It's something that we've talked about in terms of definitions over the last couple of days, but we haven't seen it visually. Now we're seeing it. Okay, so this is a difference between products and reactants. What's that going to be? That's your enthalpy. And what's the symbol for enthalpy, guys? Yeah, there's your delta H. Okay? That's your enthalpy difference. So we can calculate the enthalpy. Now remember, it's always delta H equals H of the products minus H of the reactants. All right, so what's our heat of the products, guys? Nope. 10. 10, right? Because it's products minus reactants. Reactants are 45. So what's our delta H going to be? Does that make sense, guys, that it's negative 35? Yes. Absolutely. Why? Because this is exothermic. And it is stable, right? This would be a stable reaction because it's got a large negative delta H. Okay? Now, I'm going to draw in a red line. If you have a different color, I would encourage you to do that. If you don't, just a dotted line might help you. I'm going to draw a new reaction pathway. Exactly. That's exactly what I was showing you guys. This is what a catalyst does in real time. So you know, and you've heard that, through all your science classes, that a catalyst speeds up a reaction. Well, why does it do that? This red line, guys, is symbolizing what a catalyst does. What does it do in turn? Alex? Exactly, guys. It lowers this hump that you've got to get over. It lowers that activation energy. Now, it does also... I'm sorry, I drew it in the wrong spot. Now your activation energy, guys, is right here. We don't have a dotted line to it. We could estimate it, but we don't need to. But we can see, hey, now my EA has gotten so much smaller, this reaction is going to speed up. It provides an alternate path for the reaction to take that speeds it up. It uses less energy. Okay? So, again, you know that, hey, it speeds up a reaction, but this is what it actually does, why it speeds it up. It creates a smaller hill, in a sense, for that energy portion to get over. Okay? So I want you guys just to add that in there. Again, just to drive that home. Catalyst speeds up reaction because it decreases the activation energy. Thermic. All right, so I would encourage you guys, first thing, when you see a reaction like this, draw dotted lines in there just to kind of give you guys some help. To kind of, be able to eyeball where things are. Let's just throw some random ones in. We'll throw the same ones in there since this is just the reverse reaction. 100 kilojoules, 45 kilojoules, and 10 kilojoules. Take a couple minutes, guys. Go through and label the same parts. So we have the reverse reaction, which again, this makes it an endothermic. But notice, guys, the spots are the same. Arrow heights may be a little bit different than what they were, just because of the way our pathway was, but everything else is still in the same spot. Okay? Potential energies below the graph, activation energies are above the graph. Again, delta H, same thing. It's always products minus the reactants. So in this case, it's going to be the products, which is 45 minus 10 for our reactants. So it should make sense that we have a positive energy here, because we had to put energy in the system. Guys, we put 90 kilojoules of energy into this system to get over the hump, get over the activated complex. Do we get all of that back? No. Okay, in the last one, we got more back than what we put in. Here, we don't even get close to that. How much back? okay, that we put into it. So if I drew a catalyst in, again, it would look something like this. Okay, lowers that activated complex, that activation energy. All right, which is why it speeds it up. Questions? I anticipate you seeing some types of questions, guys, like this on your Regents exam. Let's just move on. We'll do a few more notes. So, how does this, going back, guys, to fill in those blanks there? The activated complex is lowered, which means the activated energy is lowered, which means the reaction pathway is shortened. So those are those three blanks that we skipped over a minute or two ago. Okay? Just to really drive that home, that's what a catalyst does. Does it take part in the rest of the reaction? Not exactly. Okay, because you can reclaim the catalyst. So in a lot of industrial processes, they use very expensive catalysts like rhenium and titanium and platinum. And they can reclaim those after they've undergone a process and reuse them over and over again. Eventually they will lose their ability to catalyze, but you can still get your money's worth out of it. So they look to use those a lot in industrial processes. All right, so now, guys, talking about equilibrium. So this is on page number, that one right there, I think. Nope. This page right here. 11. Page 11 in your packet. Okay? Guys, equilibrium occurs. This is what we started seeing yesterday in the lab. When were you done with the straws? With the first one that we did. Not the second one that had the different sizes that just didn't work out.
3 times the same.
Right? When you had the same volume after every time. Now, after the first trial, were the volumes equal to each other in both cylinders? No, they were close, though. Were they close? Okay. But they stayed the same. Because, guys, when you took one straw and put it into the other one and the other one back into the first beaker or cylinder, all right, the rate of the forward reaction equaled the rate of the reverse reaction. Okay? That's what equilibrium means. Now, we think equal. Amounts have to be equal, but that's not always the case. It just means that, hey, when you go in the forward direction and then you go back in the reverse direction, okay, it's the same. The numbers would be the same in terms of staying put, staying stationary, not necessarily equal. So it would be like, it could be 15 and 15, but it could be 10 and 20. But as long as those numbers are the same each time. Okay, doesn't necessarily mean that the numbers have to be equal to one another. Tony, you had a question.
Oh, no, I answered.
You answered? Okay, awesome. So, equilibrium, guys, we know by now it's a double arrow. There's many different ways that you can write those. It could be 2 arrows above each other. It could be 1 arrow. You get the idea with that. Equilibrium is dynamic. Okay, that means it's constantly changing or fluctuating. Okay. It's a fluid process. We've thought up until this point that once I mix something together, it's over, it's done. Okay? For some of our reactions, it's been that way. But, especially those acid-base ones. Think back to the titration lab before break. We did the titration until it turned pink. Could we get it back to be clear again? Did any of you guys get it to be clear again? After you kind of mix all your stuff together? Right. Yeah, you add more acid, it turns back to being colorless. Then you add more base. So we can keep going back and forth, so it's fluid, okay? It can be constantly changing. Equilibrium, guys, means that the reactant and product concentrations are constant. That's what we're talking about when the numbers, quote unquote, stay the same. Doesn't mean they're equal, they're just constant after you keep running trials. Okay? And that's that last point. Star it, highlight it if you have a highlighter. Circle it in your notes. Equilibrium does not mean that the reactant and product concentrations are equal. It just means that they stay constant. Okay? They remain constant. We have to define equilibrium in terms of reactant and product concentrations. Okay? In terms of the concentrations, how do we define equilibrium? This is what we got to think. What's that?
Did you ever have someone in your old school get busted?
So when in terms of the rate of the forward and reverse reaction, guys, it's when the rate of the forward equals the rate of the reverse. And we're going to talk more about this tomorrow and write the actual expressions. They're called K expressions, okay? Easy to write, and then that's where we'd have a little bit of the math, okay? Equilibrium in terms of reactant and product concentrations. The concentration guys, again, they can be different in terms of what their amounts are, but remember, they remain constant. So they may be equal in terms of their concentrations. You might have, for example, yesterday, 25 or 15 mils of water in cylinder A, 10 mils in cylinder B. They're different amounts, but after you do every transfer, they still remain that same 15 mils and that 10 mils. That's what it means in terms of concentration. So the concentrations remain constant after as you're reacting. In terms of the reaction rates, the forward rate equals the reverse rate, which leads to the concentrations being the same. So they go hand in hand. Make sure you guys can understand and be able to explain that. All right, types of equilibrium, guys. Last few things before we kind of move on tomorrow. They all occur, guys, in closed systems. Why do you think they have to be in closed systems? What do I mean by a closed system? Let's start there. Exactly, guys. If you're open, like this room right here is an open classroom because other factors can keep coming in and have impacts. We want it to be a closed system so that it's just the pieces in the reaction taking place. We don't want, pressure to have an impact. We don't want other variables changing. We want just the reaction rates to be affected. So it's all about those equal rates. So physical equilibrium, guys, involves physical changes where you have phase change examples. So, for example, solid to liquid, the rate of melting equals the rate of freezing. We know from KMT that happens at 0 degrees Celsius. Or liquid to gas, the rate of evaporation equals the rate of condensation. All right, sealed container at 100 degrees Celsius. So we've talked about these two types of things already. Chemical equilibrium, guys, that's what we'll start talking about tomorrow.